Welcome back to Simple Quant. Today we will discuss all the basics of probability. We will begin this video by introducing a difficult probability question, and then throughout the video we will build our knowledge from scratch so that we can solve this problem at the end. Let's get started. This is Mr. Goopy. Mr. Goopy and his wife go on a dating show, and along with 5 other couples, they play wife swap. Now how wife swap works is all the wives are randomly assigned to a new partner. They all get swapped around any which way. Now our question for today is, if all wives are randomly assigned, what's the probability exactly 3 are paired with their husband? Now this is a difficult question, so we'll slowly build our way up to it. Today's video is the second video in a 12-video series covering all of college probability. Today we will cover sample spaces, basic definitions of probability, DeMorgan's law, the axioms of probability, and we'll conclude with inclusion-exclusion. By the end, we will have enough tools to solve the original wife swap question. Our first topic is the sample space. What is a sample space? The sample space is the set of all possible outcomes. This helps distinguish all the possible scenarios in which events can happen. This lays the foundation for all of probability. A sample space is usually denoted with the big letter S. Now what's an example? Well, what is the sample space of your wife cheating on you? Now the question here is essentially, how many outcomes are there if you suspect your wife is cheating on you? Well, an example sample space could be, one outcome is that she's cheating, and another outcome is that it's just a guy best friend. This is an example sample space. It's just capturing all the possible outcomes. Now for another example, what is the sample space of a die roll? Now when you roll a die, there are 6 possible outcomes. You roll a 1, 2, 3, 4, 5, or 6. Thus, our sample space can be written as follows. S equals the set of 1, 2, 3, 4, 5, and 6. Now for another example, what is the sample space of 2 consecutive coin flips? Well, all the possible outcomes of 2 consecutive coin flips are as follows. You can get 2 heads in a row, a heads then a tails then a head, or even 2 tails in a row. So our sample space can be written as follows. All these pairs of heads heads, heads tails, tails heads, and tails tails. That's our sample space. That's our sample space. That's our sample space. That's our sample. The first thing we need to talk about is an event. An event is a subset of a sample space and is often denoted with a capital E, but can also be noted with any other variable you'd like. Now, what are some examples of an event? So one thing we could say is, if the sample space is S, any outcome of a die roll, one possible event from the sample space could be the event that you roll a 1. Or maybe another one, the event that you roll an even number. The whole idea of an event is just a way to categorize a couple terms out of a sample space. Now for some more examples, if we look back at our sample space of 2 consecutive flips, one event could be the event that you roll a heads on the first flip. And that would give you an event set of these 2 terms right there. Now lastly, one thing to touch on is this term right here. You might see this in textbooks. This is called the null set. It is the set that contains 0 outcomes. So if you ever see this, there's no possible events from that sample space. The next important topic to cover is called equal likelihood. And this is a pretty intuitive concept. If a sample space has n elements that are all equally likely, each has probability 1 over n. The main idea here is, if there's n outcomes and all of them are equally likely, each of them has a probability of 1 over n. And using this principle, in general, the probability of any event is the same as the number of outcomes where A is true or A happens, divided by the number of total possible outcomes. Now this seems quite intuitive. The probability that something happens is a number of ways that it can happen divided by the total number of things that could happen. But to really make sure we understand this concept, let's do some practice problems. What is the probability that the sum of 2 die rolls is 5? Well, we saw from the previous slide that the probability that an event happens is the number of ways an event can happen over the total number of possible outcomes. So what are the total number of possible outcomes? That's just the total number of outcomes when you roll 2 dice. And that happens to be 36 possible outcomes. You have 6 possibilities for the first die and another 6 possibilities for the second die, giving you a total of 36 possibilities. Now, what is the number of ways that you can roll a 5 with 2 die rolls? Well, you could roll a 2, then a 3, or you could roll a 3, then a 2, or you could roll a 4, then a 1, or a 1, then a 4. So there are 4 possible ways to roll 2 die that sum to 5. Thus, our final probability is 4 over 36, which is the same thing as 1/9. Now for another practice problem, what is the probability that you get 4 heads in 9 coin flips? Well, let's just use the same strategy. We know the probability of an event is the number of ways that event can occur divided by the total number of possible outcomes. Now, how many possible outcomes are there? Well, for each flip, there's 2 possible outcomes, a head or a tail. So if we do 9 total coin flips, there are 2 to the 9th total possibilities in our sample space. Now the question is, how many of those 2 to the 9th probabilities in our sample space have exactly 4 heads? And the actual way to count how many times we could have 4 heads in 9 coin flips is the same logic as how many ways are there to choose 4 heads out of 9 flips. So the number of ways that we can have 4 heads in 9 coin flips is 9 choose 4. Thus, our final answer is 9 choose 4 over 2 to the 9th. So that actually covers all we need to know about sample spaces. Now let's move on to some basic definitions. The first important definition is called the union. And the union symbol looks like a big U. Its definition is the elements in at least one of A or B. Another way to think about it is just the word or. If you read this expression right here, it's basically saying, is the outcome you want in either A or B? In Venn diagram terms, union A or B is the same as having any segment in at least A or B, which is the whole Venn diagram. The next important term is called the intersection, and the intersection looks like an upside down U, and it means elements in both A and B. The key word here is and. Essentially, it asks that the term you want is included in both set A and set B. If you look at a Venn diagram, A intersect B is the little segment in the middle where A and B overlap. The next important term is called the complement, and it can be written either with a little c on top or with a bar on top. And the definition is the elements in S but not in A. The main words here are not in. If you see the complement symbol, just think anything that's not in that set is part of the complement. So if we look at a Venn diagram, for example, this would be a complement because it's everything in the Venn diagram that is not included in the set A. Finally, we have minus, and minus is pretty intuitive. It means elements in A that are not in B. So basically, you subtract all the elements of B from A, and what's left is the definition of minus. So if we look, for example, at this Venn diagram, this would be A minus B, because it's everything included in A after subtracting all the parts that are in. So for an example of everything that you've just seen, we have 2 sets A and B in the sample space. An example of A intersect B complement is all the parts of A that are not included in B. A intersect B is the overlap between the 2 sets. A complement intersect B is all the parts that are in B that are not included in A. And finally, A complement intersect B complement is all the stuff in the sample space that is not included in either set, which is just everything outside these 2 circles. Finally, we have a few more properties that also hold with all these set operations, and those are the commutative property, where A union B equals B union A, or A intersect B equals B intersect A, and so on. Any way you flip around the two terms with any of those symbols we just mentioned will be valid. Same thing goes for associative. Any way you orient two parentheses around these set operations will still be the same. And finally, they're also distributive. So for example, you can distribute this intersection symbol on this A union B, and you'd get A intersect C union B intersect C. So let's look at a practice problem that really hammers home all these concepts we just learned in our basic definition section. Let A equal the set of 1A, 3, 3, 4H, and B, 7. Let B equal the set of 7, 5, 4H, and 2J. First, let's find A union B. A union B is just the set that contains all elements from both sets. So that will look like this. It has all the elements that are in both sets, and the overlapped one, the 4H, ends up just being in this final set one time. So that's what A union B looks like. Now let's take a look at A intersect B. So intersection, remember, is all the terms that are in both A and B. So in our example, the only terms that are in both A and B is 4H. So A intersect B is the same as the set containing 4H. Now let's look at A complement. A complement, remember, is all the terms in our sample space that are not included in A. So what's included in A are these four terms right here. So everything that's not included in A are the parts of B that are not overlapping with A. So A complement is 7, 5, and 2J. Finally, we have A minus B, which are all the terms that are left in A after you subtract all the terms that are in B as well. So the only term that is in both A and B is 4H. So when you subtract B from A, you should be left with 1A, 3, 3, and B, 7. So that's what we get for A minus B. So with that, we've now covered our first two topics in our basics of probability, both sample spaces and basic definitions. With our foundation set, let's now learn about DeMorgan's law. What is DeMorgan's law? DeMorgan's law is a concept where we distribute a complement around parentheses. So for example, if we take the complement of A union B, that's actually the same thing as A complement intersect B complement. And similarly, if we take the complement of A intersect B, we get A complement union B complement. Now let's look at some English examples to see how this makes sense. So if you were looking for the complement of he's smart and handsome, so you'd say he's not smart or handsome, that's the same logical equivalent in English to he's not smart and he's not handsome. So right here we had our A union B complement is the same as A complement and B complement. Now for another example, she's not hot and cheese loving. So our thing in parentheses right here is hot and cheese loving. That's A intersect B. But we have this not right here. So that's the complement. So what's the complement of A intersect B? That's A complement or B complement. So this statement right here is logically equivalent to she's not hot or she's not cheese loving. So now you try. If A is the event that he's nice and B is the event that he's rich, what is A union B complement? Well, using DeMorgan's law, we realize that A union B complement is the same as A complement intersect B complement. And if we flip he's nice into A complement, that'd be he's not nice. And if we flip B he's rich to B complement, that means he's poor. So our answer to this question is he's mean and he's poor. So that covers DeMorgan's law. So we've now covered our first 3 topics. Next, we'll move on to the axioms of probability. What are the axioms of probability? The axioms of probability are 3 specific rules that help us utilize all that we just learned about sample spaces, definitions, and DeMorgan's law. The first of the axioms is as follows. The probability of any event is always between 0 and 1. Now this makes a lot of sense logically. If something has probability 1, that means it's guaranteed to happen. It doesn't really make sense to say an event will happen with a 150% chance. 100% is the max, so that's why all probabilities are capped at 1. And by the same logic, it doesn't make sense to say an event has a less than 0 probability of occurring. The lowest probability anything can have of occurring must be 0. This simple rule reflects these facts and basically tells us all probabilities are between 0 and 1. Our next axiom is that the probability of the sample space is always equal to 1. So why does this make sense? Well, the sample space encompasses all possible outcomes. So surely there's a 100% chance that one of these outcomes comes true. And finally, our third axiom is a little more complicated looking, but I'll break it down in more simple terms. But the main idea is that the probability of the union of any event is the same as the sum of all probabilities of those individual events, when all these events are mutually exclusive. Now that's a little confusing, so let's break down what that means. So the first thing to talk about is what does mutually exclusive mean? Mutually exclusive essentially means the outcome of one thing has no bearing on the outcome of another. So for example, 2 mutually exclusive events might be the outcome of a die roll and the outcome of a coin flip. The die roll has no bearing on the result of the coin flip. Now using the die roll and coin flip example, let's look at what this means. So let's say A is the event that there's a die roll that equals 4. And let's say B is the event that a coin flip is heads. So these 2 events are mutually exclusive. And what the axiom of probability states is that the probability of A or B equals the probability of A plus the probability of B. It's basically saying the probability that you either roll a 4 or you flip a heads is the same as the probability that you roll a die and get a 4 plus the probability that you flip a coin and get heads. If you're still a little bit confused, don't worry, let's do a practice problem right here. Let's say the probability of A equals 0.3, and let's say the probability of B equals 0.2, and our sample space contains A, B, and C, which are all mutually exclusive events. What is the probability of A or B? Well, we know the probability of A or B from axiom 3 is the same as probability of A plus probability of B. That is because these 2 events are mutually exclusive. So our solution for the probability of A or B would be 0.3 plus 0.2, and that equals 0.5. So now that we've determined that probability of A or B equals 0.5, what is the probability of C? Well, we know the entire sample space contains A, B, and C. So the only probability that it's C is if it's not A or B. So if the probability of A or B is 0.5, then the probability that it's not A or B must be 1 minus 0.5 equals 0.5. So C must also have a probability of 0.5. So what are some useful things that we learn from these axioms? Well, the first thing we learn is the probability of A complement will always equal 1 minus the probability of A. And this kind of makes sense because 1 is the probability of the entire sample space. And if we have probability of A complement plus probability of A, these 2 terms right here basically equal the probability of the whole sample space. Because if you add the event that A occurs plus all the events that A doesn't occur, that's all the possible events. So this term right here equals 1. And if we do a little bit of rearranging and subtract the probability of A from both sides of this equation, we're left with the probability of A complement equals 1 minus probability of A. So this is an important equation that you will continuously use in all of probability. Now the second result from our axioms is that if A is a subset of B, then the probability of A is less than or equal to the probability of B. Now this concept can be easily seen if we draw a diagram. If A is a subset of B, A will always be inside of all possible outcomes of B. And since B has more outcomes than A and also includes all the outcomes that A includes, there will always be a higher chance that B occurs than A. So that's where this comes from. And finally, the last consequence of our axioms is the probability of A and B is less than or equal to the probability of A. And this is a notation you might see where you just have two letters next to each other. That's the same as A intersect B. So why does this make sense? Probability of A intersect B is the amount that A overlaps with B, and there's no possible way that A overlaps with another set and that overlapped section is bigger than A itself. So that's how we derive this from the axioms. So finally, let's look at some practice problems for the axioms of probability. If Geronimo is either fine or chopped, and he's fine 4% of the time, how often is he chopped? Well, let's say A is the event that he's fine, and then A complement is the event that he's not fine. And in this case, all Geronimo can be is either fine or chopped. So our sample space is only fine or chopped. Thus, probability of S equals probability of A plus probability of A complement, and that's the same as 1 equals probability of A, which is that he's fine, 4%, 0.04 plus probability of AC, which is he's not fine. So our final answer is probability AC equals probability he's chopped equals 1 minus 0.04 equals 0.96. Geronimo is chopped 96% of the time. So with that, we have concluded our axioms of probability coverage, and now we can finally move on to our final topic, inclusion, exclusion. So what is inclusion, exclusion? Inclusion, exclusion is the whole concept of trying to figure out what we do with unions if they are not mutually exclusive. So for example, if A and B are overlapping, how can we find the probability of A or B? So essentially our goal here is to figure out how much it takes to fill in all parts of this Venn diagram exactly once. So let's take a look at what that means. So for example, if we have probability of A plus probability of B, if we fill in our Venn diagram, we have everything covered except this little intersection in the middle is actually covered twice. So we overcounted a little. That means probability of A or B must be a little bit less than the probability of A plus the probability of B. Now, how much less is that, you ask? Well, it's exactly this little intersection less than the probability of A plus the probability of B. So to actually find the probability of A union B, we must subtract the probability of A intersect B, which is that little segment in the middle. So our final answer for the probability of A union B when they are not mutually exclusive is this whole term right here. The probability of A plus the probability of B minus the probability of A intersect B. So here's a practice problem utilizing what we just learned in inclusion exclusion with just two sets. If you roll a 6-sided die, what's the probability you roll either an even number or a number greater than 3? Now the main thing to emphasize here is that these two events, the event you roll an even number and the event you roll a number greater than 3, are not mutually exclusive. For example, if you roll a 4, that is both an even number and greater than 3. The outcome of your first event influenced the outcome of your second event. Thus, the probability of A union B does not only equal the probability of A plus the probability of B, it actually equals the probability of A plus the probability of B minus that overlap part, which is the probability of A intersect B. So using this information, let's solve this problem. So let's say that A is the event that you roll an even number. What is the probability of A? Well, the probability of A is just the event you roll an even number. So in our 6 possible chances, you could roll a 2, you could roll a 4, or you could roll a 6. That's 3 out of 6. So there's a 1/2 chance that you roll an even number. So P of A equals 1/2. So we have P of A equals 1/2. Now what is P of B? What's the probability that we roll a number greater than 3? Well, out of our 6 possible outcomes, we could roll a 4, a 5, or a 6 that are all greater than 3. So our probability that you roll a number greater than 3 is 3 over 6, which again gives 1/2. So the probability of B equals 1/2. Now finally, what's the probability of A intersect B? Well, the probability of A intersect B is the probability that you get both an even number that's greater than 3. So out of these 6 possible outcomes, 4 and 6 are the only possible outcomes that give you an even number that's greater than 3. So the probability of A intersect B equals 2 over 6 equals 1/3. So the probability of A intersect B equals 1/3. So now let's solve the problem. We know that the solution we want is the probability of A union B, the probability that the die roll is either even or greater than 3. And the way we solve this is with this equation right here. Probability of A plus probability of B minus probability of A intersect B. We just calculated that the probability of A and B are both 1/2, and the probability that A intersect B is 1/3. So our final solution is 1/2 plus 1/2 minus 1/3, which gives us an answer of 2/3. The probability you roll either an even number or a number greater than 3 on one die roll is 2/3. So now what if you wanted to make inclusion exclusion a little more complicated? How would you calculate the probability of A union B union C? What's the probability that you get at least A or at least B or at least C? So again, if we have a triple Venn diagram right here, we'd be looking for what probabilities do we add together to fill in each part of the Venn diagram exactly once. So to start, we could do what we did with the last problem. We add all the individual probabilities. We fill in each of these circles exactly once. So that means we shaded each of the big circles 1 time, each of these intersection segments 2 times, and this middle section 3 times. So we're still overcounting by quite a bit. Let's see how we can get rid of this overcounting. Let's try subtracting those leaf segments. So that'll be subtracting the probability of A and B, the probability of A and C, and the probability of B and C. So now each of these leaf segments are each filled in exactly once. The only issue is that we've subtracted too many out of the center, and we're left with 0 shading in the center. So how do we fix that? The final step in this process is to add back that little centerpiece, which is the probability of all 3 events, A, B, and C, happening simultaneously. So if we add back that probability, we have now successfully figured out the probability of A union B union C. And using this intuition, we are now able to talk about the general principle of inclusion-exclusion. How do you find the probability of the unions of many, many sets? It looks quite complicated in this notation with all these negatives and all these variables, but I'm going to try to simplify it in a way that makes sense to me. The main idea of this is to start by adding all the singles, so all the probabilities of the n events. And the number of these terms that you have to add will be n choose 1. Then you subtract all the doubles. Those are all the parts that were counted twice. And you'll end up with n choose 2 of these such terms. Then you add back the triples, and there will be n choose 3 of these such terms, and so on and so on. So for quadruples, you'd subtract all the n choose 4 of these terms. So the main pattern is as follows. you keep increasing the size of the intersection of these sets. So it'll go singles, doubles, triples, quadruples, and so on. And then each time you alternate between adding and subtracting. So for example, if we look back at our union of 3 events, we added all the singles, then we subtracted all the possible doubles, and we added back all the possible triples. And that correctly shades all the probability of the union exactly once. And with that, we've successfully covered all the important topics in basic probability. We've covered sample spaces, basic definitions, DeMorgan's law, the axioms of probability, and the principle of inclusion-exclusion. To conclude, let's return to our wife swap game show. So as a refresher of this question, if all wives are randomly assigned among 6 pairs, what's the probability exactly 3 are paired with their husband? So using our definition for how to calculate probability, we know the probability of an event is equivalent to the number of ways that event can occur divided by the number of total outcomes that can occur. So in our scenario right here, we are trying to figure out the number of ways to pair the 3 correct wives as the numerator, and the total number of ways to pair the wives will be our denominator. So we got to find these 2 terms right here. So to start, let's look at S, the total number of possible pairings, the total number of outcomes in our sample space. How many ways are there to pair these 6 wives with these 6 husbands? Well, if we label the husbands A, B, C, D, E, and F, the first husband can end up with any of these 6. So the first guy will have 6 options. Let's say, for example, that he gets paired with this one right here. Now there are 5 options left for the second person. So there are 5 options left for husband B. And then out of the remaining 4, there are 4 remaining wives left for option C. And this pattern goes down the line until we end up with exactly 6 times 5 times 4 times 3 times 2 times 1 possible pairings of husbands and wives. This is the same as 6 factorial. So we have that S equals 6 factorial. So if we go back to our equation right here, the number of ways to pair the wives is 6 factorial. Now all we need to do is find A. How many ways are there to pair exactly 3 correct wives? Well, to start, let's choose 3 wives that are correctly paired, and then we can figure out something from that. So for example, let's imagine the first 3 wives are all correctly paired. Now, how many ways can these exact wives be correctly paired? Well, that's the same thing as asking, how many ways can we reorder these 3 wives with these 3 husbands such that none of them are correctly paired up? Because if any of them are correctly paired up, we now have more than 3 exact pairings of husband and wife. So how can we order these 3 wives with these 3 husbands so that none of them match up? We have one example like this, and we have one more example like this. So what does that tell us? It tells us that there are exactly 2 factorial outcomes where exactly 3 specific husbands have their correct wife. For any 3 husbands we choose to be the correct ones, there are 2 possible outcomes in which these husbands can be paired with their correct wife. So now the second part of our question of finding all the possible 3 pairing outcomes turns into how many ways can we choose these specific men? We know each correct pairing with any 3 men has 2 possible outcomes. So now we need to know how many ways can we choose these 3 men. So if we have 6 men and we want to choose exactly 3 of them with no repeats, that gives us 6 choose 3 possible ways to find exactly 3 men out of this group. Thus, the number of ways to exactly have 3 correct wives, this A term right here, is 6 choose 3 times 2 factorial. It's the number of ways to choose the 3 men times the number of ways to have exactly 3 correct wives with those 3 chosen men. So with this knowledge, we can rewrite our original probability calculation as 6 choose 3 times 2 factorial over 6 factorial. Further simplifying, we know 6 choose 3 is the same as 6 factorial divided by 3 factorial times 3 factorial. We can simplify down to 2 factorial over 3 factorial times 3 factorial. And that again simplifies even further to 2 divided by 6 times 6, which is 2 divided by 36. And that gives us a final answer of 1/18. If all wives are randomly assigned, the probability exactly 3 are paired with their husband is 1/18. And with that, we have successfully completed our coverage of all of basic probability. Thank you so much for watching. If you have any questions about anything, you have any comments, any feedback, I'd love to hear it in the comment section below. I'll be sure to respond to any questions you might have about the content. And if you enjoyed this video and you learned something, I'd really appreciate if you subscribed. Thank you very much.